So, picking up where we left off. More analysis. Alright, so we have this histogram. On the SAT, I want you to note that histograms always have the same kind of setup where the bar, the left endpoint's included and the right one's not. So this first bar represents from 10 hours to 19 hours. Okay, and then the next one starts at 20 and goes up to 29, 30 to 39, 40 to 49, 60 to 69. Okay, that way you're not wondering, okay, where's 20 included? They usually follow that same pattern. All right, and they explain it in the question. The histogram of the first bar represents all workers who worked at least 10 hours, but less than 20. That means 20 is not included in that first bar. Everything under it is included. Okay, so it asks which of the following median and mean could be the amount of, which of the following could be the median and mean for the amount of time worked in hours for the 40 employees. So a couple things I want you to pick up on. One, 40 employees. Okay? That means if I add up the total of each of the bars, it totals 40. Alright? So 40 people is the total of each of the bars. Okay? The other thing is could be. Not is, could be. Okay, which ones are reasonable? And the reason they're asking the could be is twofold. One, for mean and for standard deviation, too long to calculate, so they're not going to have you calculate those exact values. What they want you to be able to do is identify either what a reasonable value would be based on looking at the trend, or they want you to be able to identify the effect that the graph has on those values or what those values have on the data set. Okay? So you're not going to have to calculate mean. You're not going to have to calculate standard deviation, but you need to understand what those things represent. So first we're going to start with median. What is the median of a data set? The middle number. Okay? So if I have 40 employees, what's the middle number going to be? 20. Okay, so I need to figure out what the 20th number is. Okay, I need to know what the 20th number is, and that's going to tell me what my median is. Okay, so my first bar graph includes the first 6 values. Okay, so I have 1, 2, 3, 4, 5, 6 employees, and then I can continue into the second bar, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So my median is somewhere in that bar. Now, I don't know exactly what value is because I don't know what each individual data point is. I could have 5 people that worked 20 hours and then 7 people that worked 23 hours and then, one person worked 29 hours. I don't know what those individual data points are. Okay? So I can't find the exact median, but I know that it has to be somewhere in this bar. All right? From 20 to 29. So I can go ahead and I can eliminate one of these median values. Which one? Okay? I can eliminate option D because that median, let's draw on it. Nope. Okay. There we go. Okay? That's outside of where I expect my median to be. So I can get rid of D. All right? Now, I still have 3 options, and I have to look at the mean to pick what my answer is going to be, either A, B, or C. Okay? Now, again, I can't calculate the mean. I don't have enough information. So I have to think about, okay, well, what effect is the data set going to have on my mean? Okay? So I have a median value somewhere in the 20s, right? But I still have a lot of data sets over on the right. So that's going to take my mean and it's going to shift it further to the right. So my mean is probably going to be to the right of my median value. Because I have all of these higher values pulling that average higher and higher. So which of those options makes the most sense for what our mean is going to be? C. Okay? Because For B, the mean is less than the median. That is highly, highly unlikely in this case because I have so many values further right of my median. It's very unlikely that my mean will be less than my median in this case. Okay? Also, my median is 22, my mean is 3. Those are very, very close together. Again, that's going to be highly unlikely that the mean is going to be that close to the median. Again, with all of these values, it's going to pull it more and more to the right. 32 makes sense, though, okay, because it's still close to my 20s, but it's more centralized, okay? When you have data that's far away from your center, it affects the mean and it pulls it in that direction, okay? Especially when you have what we call outliers, all right? Data points that are really far from the center are going to pull your mean away from where your median is, all right? Median's not affected by outliers, but your mean is. And so if you have outliers in one direction or the other, it's going to drag that mean in the other direction, leaving us with a reasonable option for those values. We don't know for sure that they are. We don't have enough information, but that option fits the best. All right? So again, not having to calculate mean, but understanding the effect that data has on the mean. Understanding what the mean represents. It represents average. Now we have a two-way table. Right? Two-way tables can be frustrating from time to time because there's a lot of information there, and usually we only need little bits of it. So it's really important with a two-way table that you take the time to read the graph to see what's being talked about, especially in each row and each column. On a two-way table, the last row and the last column always represents the totals, and this very, very last cell is the total of everything. And then your rows and columns represent different things. So our rows here represent, so we have a store with 10,000 people a week that come through the store. All right? The first row represents the number of customers that attempt to shoplift. Naughty, naughty. Bad people. Okay? So, of the customers that attempt to shoplift, there's 24 total. 21, the alarm went off, and 3, the alarm did not. Okay? That's what each of those cells represents, and the total is represented at the end. Customers that did not attempt to shoplift. Good for them. Law-abiding citizens. Okay? There was a total of 9,976. Most people are law-abiding citizens, so that makes sense. Now, of those people, most of them, 9,941, the alarm didn't go off when they left. Normal day. All right? But for 35 of them, the alarm did sound. It was a false alarm. It happens sometimes. You go to Target, buy something, you walk out, the alarm goes off. I swear I didn't steal anything. I promise. Here's my receipt. Okay? It happens. All right? The columns represent the same data in a different perspective. The column is, okay, how often does the alarm sound or how often does it not sound? It went off 56 times. Again, 21 was actual thieves, 35 was false alarms, and it didn't go off 9,944 times. 3 of the times someone got away with stealing, and then the other 9,941 times was just a normal day. People got what they needed and left. So there's a lot of information here. When we're solving for a certain probability, we only need 2 numbers out of all of those. So we need to be very, very careful about picking the correct 2 numbers. So according to the manager's estimates, if the alarm sounds, okay, what row or column tells me if the alarm sounds? That first one, that first column. So this is the column that I'm concerned with. Okay, if the alarm sounds. How many times did the alarm sound? 56. Okay? So if the alarm sounds, which happened 56 times, for a customer, what is the probability that the customer did not attempt to shoplift? So how many times did someone not attempt to shoplift of the times that the alarm sounded? Okay? So again, I'm concerned with this column and this column only. The probability that a customer did not attempt to shoplift when the alarm did go off. So I have a probability of 35 over 56. Okay? So you can do the division, you'll get a decimal, turn your decimal into a percent. But there's only one option up here that makes any reasonable amount of sense without even having to use my calculator. Okay? Because A is less than 1%, B is less than 1%, C is less than 1%. Okay? 35 over 56 is about half. It's approximately half. So we would want to make sure that, hey, let's pick a value that's close to half. Well, A, B, and C aren't anywhere close. They're all less than a 1% chance, which is very low. Those were all taken out of one of the larger totals, taking a number and dividing it by one of the larger totals. And so that's how you get those incorrect values. 62.5%, 35 divided by 56, that's what you get. Okay? You could do the actual division. But again, a lot of times, just want you to be able to make an educated guess, and you should be able to narrow down your options. And again, it'll save you time test. They don't want you taking 10 minutes per question. All right, a couple minutes per question. The questions are designed that way. Okay, so we talked about probability. Finding probability is the ratio of the desired outcome over the total possible outcomes. Now, when we're dealing with a two-way table, we need to determine what total we're thinking about. Okay, we have to focus on the total of alarms sounding, not the total of everything, but just the total for that specific column. The number of favorable or desired outcomes, okay, it doesn't have to be a good thing, quote unquote, it's just what is the outcome that we're focusing on. And that division gives us our probability. And then within our statistics area, we have mean, median, and mode, or what we call measures of center. They give us typical values, what we would expect from the data set as normal or typical or common. Mean, all right, add all your numbers, divide by the total. You're not going to have to do that on the SAT unless it's a really small data set, but they want you to understand the effect that mean has and how different numbers will affect that. Okay, we talked about outliers. If I have an average score on a test of 85, but some kid just flunks it, 0, done, nothing right, that's going to bring that average down. It's not necessarily representative of the entire class, but that one really low value or two really low values is going to bring down my mean. Okay? So in that case, a median might be more useful, a middle number. It's not affected by outliers. It's not affected by someone was out for 3 weeks and didn't do any homework and then came back and take the test. All right? It happens. Okay? So median is that middle value. And then mode represents what shows up the most. What's the most common? Usually better for categorical types of data. Okay? Rather than just numbers, we have data sets that include how many people own Jeeps, how many people own Camrys, how many people own, so these categorical types of data is better for the mode. And these all measure center. Okay? They measure center, what is typical for a data set. Range and standard deviation are our measures of spread. Okay? How spread out a data set is. Range is simple, the difference between the highest and the lowest. Okay? Easy one to calculate. If the highest score on a test was a 95 and the lowest score on a test was 55, I subtract those and my range is 40. Okay? So the difference between the highest and lowest value. Standard deviation has this wonderful, beautiful, awful complex formula. All right? You're not going to have to calculate on the SAT because, again, it's another thing that just takes too long. But you need to understand what it measures. Standard deviation talks about how spread out a data set is from its measure of center, usually the mean. So if you have a data set that varies widely, okay, you have a middle value, you have a mean, but you've got data spread out all the way across from really low to really high, you're going to have a large standard deviation. You have a lot of data points that are far from your measure of center. But if everything clustered together and pretty consistent, you're going to have a small standard deviation. Right? So think of it this way. A large standard deviation, I give out a test, I've got, I've got a handful of kids that got less than 10%, and a handful that got between 10 and 20, and 30 and 40. And all my data set is spread out. My mean might be in the middle, in the 50s or 60s, but I've got someone that's got scores in all of those different percents from 0 to 100. That's a large standard deviation. It's really spread out. But if the vast majority of my students scored a 70 or above on a test, okay, then my data is not going to be as spread out. That's going to be a smaller standard deviation. Okay, so those are your measures of center and spread, and again, knowing how those are affected by any given data set. Now, last one, we have a two-way table. So again, it's the same thing where the bottom row and the last column are the totals. But we're missing a bunch of information, and we need to fill in some of this information to find whatever the question's looking for. Okay? So Margot has all of her favorite paintings in the museum. She categorized them by size and dominant color. Okay? She really likes red and blue. Okay? So of the red paintings, of her favorite red paintings, she's got 4 that are small. Of her favorite blue paintings, 5 of them are large. She's got 24 favorite paintings total. Okay? Now, Margot found that 1/4 of her favorite large paintings were blue. So if 1/4 of her favorite large paintings were blue, how many large paintings does she like total? 20. How do you know that? 5 is 1/4 of the total. If we write that sentence as an equation, when I multiply by 4, I find that the total is 20. So I know 5 is 1/4 of 20. 5 is 1/4 of 20. So I know we have 20 total large paintings. That is Margot's favorites. Okay, now remember, this column has to add up to 20. So if she's got 20 large paintings total that are her favorite, 5 of them are blue, how many are red? If she's got 20 total that are her favorites, 5 of them are blue, how many are red? 15. And then this row has to add up to the total. So of her red paintings, if 15 of them are large and 4 of them are small, how many does she have total? 19. All right, now, of all of the paintings, 19 of them are red. She has a total of 24 favorites. How many of them are blue? 5. If 5 of her favorite blue paintings are large, how many are small? 0. If 20 of her favorite paintings are large, how many are small? 4. Okay, so we can look through and fill in that missing information on the two-way table. Now, only one of those numbers is important to us. How many of Margot's favorite paintings have red as the dominant color? How many of her favorite paintings are red? I'm not asking for a ratio of comparing them. I want to know how many of her favorites are red. 19. Not a probability, it's just a count. It's a number. 19 of her favorite paintings are red. Boom, done. So once I found that number, I could have stopped. But, where's the fun of that? Okay, so a lot of the stuff that we've been doing this week isn't so much with calculating as it is with reading and interpreting. Okay, you got to read the information. You got to read it carefully. Any calculations that you do, or for at least in the data analysis part, is going to be very minimal because again, it's a section called data analysis, not data calculation. All right. Questions, comments, or cool. You got 2 assignments today. You're welcome.